And for those, sorry, and the link, maybe you can share the link to the other to other friends, because I also haven't prepared the link for today class. Oh, okay. So I hope you can share the link to the others. So because I'm not feeling very well right now. Okay, so the rectifiers. So this is the definition for the rectifier, which is AC input, and then it will convert into a DC output. Okay. So converting AC, which is from mains, which is from your TNB, your power supply, AC power supply, or other AC power supply to the DC power using power diodes, or by controlling the firing angles of the thyristor. So actually in the rectifier, we only use either diodes or the thyristor. Okay, so we will not use transistors. Okay, so transistors will be not in this rectifier circuit. Okay, so the rectifier will be on the power diodes and also the thyristors. Okay, and then the input can be a single input, or it can be it can be a single phase, or it can be a three-phase system. And the output, okay, the output is a DC output, which is you have a fixed values, okay, or you have a variable values. And the application of this rectifier, you can have it in DC welding, okay, using a DC power welding. And then you have application in the DC motor drive. Okay, DC motor drive meaning that we use power electronic circuit, which is we call drive, to control the DC motor speed and also the torque. Okay, and then you can also use this in the battery charger, DC power supply, and also the high voltage DC transmission system. Okay. And actually in the rectifier for this your syllabus, we will divide it into two circuits. Okay, so the first circuit that we will discuss is the half wave, which is the control and the uncontrolled. So the control meaning that we use thyristor. So we use a signal triggering, okay, to control uh, the output voltage that we want. Okay, so by using this thyristor, we can have the output voltage to be a variable output voltage. While the second circuit here, which is still half wave but uncontrolled, so the circuit we will use a diode. So meaning that this diode, meaning that the output voltage is fixed. Okay, we cannot vary it, or we cannot change the output voltage that we want. Okay, because we use diode. The diode we cannot control the triggering. Okay, so we go for the single phase half wave rectifier. So actually in this syllabus, we use a single phase. Okay, and then after we have complete the single phase analysis, then we will go for the three phase analysis. Okay, so the uncontrolled half wave rectifier, so we go for the diode first, because this is the simplest power electronic circuit. So as you can see, this is the simplest rectifier circuit, okay, which is we use a diode, we use a single power diode, and then connected to a single AC source, and then the load right now is a pure resistive load. So as you know, for the diode, it is only turned on when the circuit is fault biased, meaning that the anode is positive compared to cathode. Okay, so meaning that only when the voltage source is positive cycle, okay, then you will see the output voltage. Because during at this positive cycle, the anode is positive. Okay, so that the diode is turned on. So right now, the V out is connected to V input. So anything, the values of the V input will appear at the terminal output. Okay, and then during the negative cycle, so the polarity is changed. So the cathode is positive and then the anode is negative. So that's why the diode is in reverse bias. Okay, reverse bias. So the diode is off. So that's why we don't have any output here. Okay, because this is off. So the output is disconnected from the input. And then this is repeated. Okay. So one cycle is actually we consider as a 2 pi. So this is considered one cycle. Okay. And because of, as you can see, in this one cycle, we have only half output only, while the other half is 0. So that's why we call this circuit as a half wave rectifiers. Okay. And this is the calculation to calculate the output voltage. We have two item here, or two parameters, which is very important in the rectifier, which is we call V average and the V out RMS. Okay, so this is the equations. Okay, so 1 over 2 pi. So this is 1 over your period. And then you need to integrate from 0 to 2 pi. Okay, but since we have only output at the positive cycle only from 0 to pi, okay, so that's why we integrate only 0 to pi only. Okay, and then the function of the voltage from 0 to pi, we have the voltage output, which is equals to V input, and then we integrate, then we have Vm over pi, or 0.318 Vm. And then for the RMS, I think this one, actually the RMS equation, so the general equation, if you refer to the chapter 1 of your textbook, which is the Daniel W. Hart, okay, textbook. So in chapter 1, he introduced all the equations that use in the power electronics. So it is good also if you can refer to that book. Okay, so the RMS output voltage, the equation is 1 over period, and then you need to integrate from 0 to the full cycle, and then the function of your output voltage, the function of your output, and then square. Okay, so that is the general equation for the RMS. If you can recall back during your SEE4433 also, I have already also show you the general equation for the RMS. Okay, and then this is simplified as a Vm over 2, which is 0.5 Vm. Okay, so this is a very important parameters. Okay, I think you need to memorize this. Okay. Oh, okay. Example 1. Okay, so example 1. So the source is sinusoidal 240 volt RMS at frequency 50 Hz. The load resistor is 20 ohm. So determine the output voltage, determine the load current, the average power absorbed by the load, and the power factor of the circuit. So I give you 10 minutes to think about it. Okay. I need to take my tablet out. I think we will stop our class at 11:30. Okay, because not feeling very well. And I think for the quiz, maybe okay at 12 noon. Okay. a very simple quiz. Okay, a very simple quiz. So through online, okay, through online e-learning platform. Okay, so the average output voltage, I think this is very simple. So this one, 240 volt RMS. Okay, and the resistor is 20 ohm. Okay, the average output voltage, if you recall from the previous slide, is VM over pi, right? So VM over pi. So you need to convert RMS into VM first. So VM is square root multiply with 240 volt. Okay, so square root multiply 240 volt over pi. So what is the answer?
$108.038.
Okay, thank you. 108.0. Okay.
108.038.
108.038. Tak dengar
Yes.
lah. Okay, tak apalah. 108. Okay. Okay. And then what about the average load current? So since this is a resistor load, okay, so the current average is V out, just a simple equation, V out average over the load. Okay. So you just 108.038 over 20 ohm. So you should get 5.4. So resistor is considered linear load. Okay, so meaning that if you recall back at this waveform, as you can see, the waveform of the current is following the waveform of the voltage, but the ratio, okay, the value might be lower than the voltage because of we know that VI is actually just a ratio V over R. Okay, so that's why. So this is actually a linear load. Okay, and then when we deal with the inductive load, which is you have R and L, so that one we consider non-linear load, and the analysis will be very complicated. Okay, and then C, the average power absorbed by the load. The average power.
Sorry, doctor, what was the answer for B?
Oh, this one, sorry, 5.4 amperes. 5.4, 0.8.038 volt, okay, over 20 ohm. Okay, just simply like that. V out average is V out average over the resistor load. Okay. Okay, C, the average power absorbed by the load.
144.
144. Macam mana dapat? 144.
Find VRMS first and then divide by resistance.
Macam mana? Can you repeat back? Afif.
Find VRMS.
VRMS.
Yes. Find it
Yes,
first.
okay.
And then
Okay.
square root.
Okay,
Then
correct. Yeah. Thank you. So just to remind you that if you see this average power, so it is not It's not actually I out average square multiply with R or V out average multiply with I out average. Okay, this is incorrect. So average power is actually referring to the P, because P is actually there is a name which is we call active power, and sometimes also we call it as average power. Okay, and usually P is actually for this kind of circuit is actually I out RMS square R, or you can use V out RMS square over R, or you use V out RMS multiply with I out RMS. Okay, we use RMS term to calculate power. So actually, usually for power, okay, even though it is for power, so we use RMS. We will not use average values. Okay, we don't use V out average or I out average to calculate power. So power calculation will always referring to RMS. Okay, so thank you, Ni Afif. Okay, so right now your P out average. So right now, you can either use I out RMS or you can use V out RMS. I think it's better to use V out RMS, right? V out RMS square over resistor. Okay, because we know V out RMS, we get the equation, right? This one, right? So that's why we use V out RMS instead of using I out RMS multiplied with R. Okay, so V out RMS, so 0.5 multiply with VM, which is square root 240 volts. Okay, over the resistor 20 ohm. Okay, should get 0.5 multiply with square root 2 multiply with 240 so over 20. So you should get, betul ke? Tadi ni Afi dapat berapa? 1.55 144.
144. Yes.
Doctor, sorry, why did we multiply by 0.5?
Yes.
Oh, sorry. Yeah, this one. V out RMS is equal to 0.5 VM.
The value we have is already in RMS, Doctor.
No. This one is 240 volt RMS. This one is V input. So right now we want V out RMS. So V out RMS is 0.5 multiply square root 2 multiply 240 volt RMS. Can you get it? The difference? So this is V input. So right now we want to get the V out RMS. This one is V input RMS. Okay, so there is a difference because this one input is a 240 volt. But the output here is like this, half wave. So we want to calculate what is your V out RMS for this waveform, which is given to you 0.5 multiply with VM. Okay, so to get your VM, so you need to square root multiply with 240 volt RMS.
Doktor, saya dapat lain. Tadi salah kira.
Yeah.
Sebab nampak
This one should get 1440 kan? Dapat? I calculate 1440 watt. Ni kena kuasa 2. Any question or unclear?
Dapat.
Doctor, if I use I square RMS multiply with R, is incorrect?
Oh, okay, this one. Okay, let me explain. Okay, so because what is the equation for P to get power in RMS?
I
You can
square
use you can use
RMS
VRMS multiply with IRMS, right?
multiply
Or
with R, yeah.
or I square RMS multiply with R, right? Or V square RMS multiply with R, right? So, but this one is a P out. So this one, we want to calculate the P out, P output. So meaning that this one must be out, must be referring to the output terminal. Okay. So you can use 3 equation. Okay. But right now, we don't have any information about how to calculate your current RMS. We don't
Yes.
have any equation. We only have equation that relate V out RMS. Okay, so that's why we are using the third equation.
There is a equation IRMS equal to VM over 2 multiply with R.
Can you repeat that?
IRMS equal to VM over 2 multiply with R.
I cannot get it. Can you what you mean? What do you mean about that?
I mean IRMS
IRMS,
equal
okay.
to VM
VM
over 2 multiply with R.
to multiply R.
2 multiply R, yes. This equation we can find IRMS by this equation.
From where did you get this equation?
One is for IRMS, is it?
Yes.
I cannot understand. Oh, I see. Oh, I see. Okay. Okay, so actually what you get here is referring to your friend. What your friend said is also correct. Oh, very slow. This one into erase. Okay, this one is also correct. Okay, because you actually derive from here. V I out RMS is actually V out RMS over R, right?
Yes.
Okay, so where V out RMS is VM over 2 and then just multiply with R. Yes, you are correct also. Okay, so you can either use this one, I out RMS, I out square RMS multiply with R, or you can use V out square RMS over R. Okay, but okay, so okay, good. This one also can be used because this is actually linear load. Okay, linear load, so meaning that it's just a ratio. Okay, so you can use formula like this. Okay, so you can use, for example, I out average. For example, I out average is V out average over R. And also you can use to calculate I out RMS, which is V out RMS over R. Both can. Okay, because this is linear load. Because R is actually a constant, right? Okay. I hope you understand. Okay, thank you very much. Yes. Okay. So the answer for this is 1440 watt. Okay. Okay, so right now this is the waveform. The waveform of the input is AC, but the waveform of the output is actually a rectified half wave. Okay, rectified half wave. So lastly, the power factor of the circuit, which is challenging part here, the most challenging part. So the power factor of the circuit, what you need to do is to use the formula, the triangular formula. So this is your power factors. So this is your S, this is your Q, and this is your P. So right now your P is 1440, right? So you need to find your apparent power. Then your power factors is actually cos theta, which is P over S.
Yes.
So 1440 watt over S. So your S should be V source RMS multiply with your I source RMS. So yeah, right now your V source RMS is 240 volt. And I source RMS is equals to your I output RMS. Okay, because you are using single loop. Okay, meaning that if this one is I out, this one is IS. So same. So if this one is 5M, so this one is also 5. So like that. Okay. So calculate for me your I out RMS, which is your friend have already calculate, which is using VM over 2R.
0.48.
Berapa eh? Untuk I out
Yes.
Berapa?
12 ampere.
12 amperes. Okay. So this one 1440 watt over 240 multiplied with 12. Zero 0.5. Is it 0.5?
0.5, yes.
Yeah. So the power factor is 0.5. So, as a conclusion for this example 1, even though as you can see, this is the simplest rectifier circuit where we convert AC power into a DC power. Okay. So the conversion, so the conversion is very simple using a diode. But okay, what I want to show you is the power quality, in terms of the power quality. The power quality is usually referring to the input side. Okay, so we want always to have our voltage and current in phase. Okay, the voltage and current is in phase. That is our power quality objective. Okay, we want to always the current and the voltage to be in phase. That is the best one. But the power electronics will what we call disturb the power quality of the input. Okay, as you can see, by using a very simple diode here, okay, it will affect the power factors. Okay, to 0.5. So 0.5 is considered very low power factors. Usually the power factor that is acceptable in the grid, okay, is around 0.8 or 0.7 above. Okay, that is the acceptable power factors. Okay, you consider this, you imagine this source, AC source is your socket, okay, 240 volt socket, your home socket, and then you connect directly with the diode. So when you have this circuit, rectifier circuit, connect directly to your AC source, so all your power factors, the grid power factors will actually affect it, okay? So 0.5 very low, and then you may have penalty from your supplier. Okay, because TNB, our TNB, Tenaga Nasional Berhad, they will penalize home residents that give the grid power factors that actually give the power factor 0.5, because it will affect a lot of things in terms of the quality, in terms of the economics and so on. Okay. So I didn't want to discuss about that, but I want to highlight that actually in the power electronics, so actually in the power system, there are two peoples. There are peoples that are more towards on the power quality. They are more concerning on power quality. And there are a group of people that use power system and then do some conversion to meet the load. Okay, this one is a power electronics people. So they will actually try to process the power, okay, convert the powers to meet the consumer demand. For example, the DC load, okay, and then the motor drive and so on. But this application of power electronics, as shown here, will affect the power quality of the input. So the people that concerning about the power quality will always what I call not happy with the power electronics people. Okay, that's why. So there are two groups in the power system: the power electronics people and the power system people. The power system people, they are usually more towards on the power quality, how to maintain the power quality and so on. The power but the power electronic is more toward the consumer, how to meet the demand of the consumer by converting the power and so on. Okay. Okay, I think that's all from me. Sorry for not to have this class in a full swing. Okay, so I think I stop here. Okay, so and then our next class, which is on Thursday, we will go for the RL load. Okay, so I think that's all from me, and please be noted that our online quiz will be at 12 noon. Okay, 12 noon. So through e-learning. Okay, very simple, straightforward. Just it's actually an objective, 5-question objective. Yes, 2 p.m. So I will change it to 12. Is it okay 2 p.m? Because I don't want to disturb. Maybe this one is co-curriculum.
12 is good.
We have Excel.
12 is okay.
I think 12, right? 12 okay, right?
12
Because yeah.
is good.
Because 2 p.m. I think you have a co-curriculum. Okay,
Yes, okay.
so 12 noon. Okay, thank you very much.
Attend this,
Assalamualaikum.
teacher.
Sorry?
Scan
Yeah,
attend.
Oh, attendant. Okay. Okay, thank you very much. Assalamualaikum and have a very good day.
Okay.
Okay.
Thank you, doctor.